So for the fixed length encoding, each of the symbol will be encoded with m number of bits. Yes. So in this case, what happens is that if there are certain symbols that are frequently occurring, for them also we are going to use m bits. For those particular symbols which are occurring rarely, that also we are using m number of bits. So to solve this, or to have a better efficient code, yes, that means a smaller length code, we have variable length encoding. So as the name says here, the code that is given to each of the symbol have a different length, that means different number of bits. And in this case, the shorter code words are given to represent the frequently occurring symbols. Yes, so those symbols which are occurring again and again, let's say you have A, E, those kind of vowels are there. So for that, they will be using something like this. Yes, these kind of symbols, so that you have only 1 or 2 bits required to represent it. Whereas where you have the less frequently occurring symbols, for those symbols, we will be using a higher length or the longer code words. Yes, so in this category, you can have Q or Z or W, those kind of words appear very less frequently, and these can have a longer code words. Yes. So a bit length here requires is 4, whereas it is 2. So if you have some particular text that you want to encode, which have, let's say, A is appearing 3 times, Q is appearing 1 time, and E is appearing 2 times, then your complete encoding will be of shorter length. Yes. So what I said was, if A is appearing 3 times, so you will be putting 3 dots. Yes. So 3 bits are required. And E is appearing 2 times, so you need to only have this, so 4 bits. Yes, this is one representation and this is the second representation. And Q, which is appearing only 1 time, let's say it is having this, so it also requires 4 bits. Whereas if we would have used m number of bits and the maximum, let's say, is 4, so we are using 4 bits. Yes, to represent A 3 times, it will be using 12 bits. E, that is 2 times, we will be using 8 bits, and Q is 1 time, so it is taking 4. So total would be 24 bits. Whereas when we are using the variable length, in this case, we have only 11 bits. Yes, so definitely a bit compression takes place when you are using a variable length encoding, and this kind of encoding is known as Morse code. Yes, so this is called as Morse code, which was primarily used. This Morse code was primarily used in telegraph code. Fine. So, but there is a problem now with this variable length coding. What is that problem? The problem is, how would you know that a particular symbol is ending here and the next symbol is starting? Because there is no delimiter in between. Yes. So for that, what do we do is, because so we cannot tell when the new symbol is there or when the bits are ending, or how many or how many bits require to represent a symbol. Yes, so this is the one problem that we have with the variable length encoding. So for that, the solution that we have is prefix free code. Yes, so what we said was the problem is that we cannot tell how many bits are there, and for that, what do we have here is so what do we have here is for the prefix code, okay, that we can have a prefix attached with each of the symbols. So let's say we have a slash here as a prefix. So after every dot, let's say we were saying that we want to represent QAE. Yes, so in that case, this can be represented by dash dash dot dash, and there is a prefix symbol, then there is a dot, there is a prefix symbol, and then there is a, so this represent Q, this represent A, this represent E. So we have to use a prefix here. So for that, what do we, because again, if we are using prefix, it is going to increase the number of bits. Yes. So what do we need here is a prefix free code. And this prefix free code, what it says is no code word is a prefix of a code word of another symbol. So we should not have any code word, yes, that can be a prefix to another code word. So in here we have dot and this, yes, whereas this is a dot. So dot becomes a prefix to this. So we should not have code words where a code word is a prefix of another code word. Yes, so I hope this becomes clear that what we mean by prefix free code. And Huffman have suggested a binary prefix code for the alphabets. So let's see what does it include. I would suggest for all of the students here. So now moving on to the Huffman uh, codes. So the logic here is that whatever the alphabet symbols are there, yes, those alphabet symbols represents the leaves in a tree. So what does it do is Huffman algorithm will generate a Huffman tree, encoding tree, as well as Huffman code. So within that Huffman tree, alphabet symbols will be the leaves, and the left edges are labeled as 0, and the right edges, I'm not talking about the nodes, I'm talking about the edges, and the right edges within the tree are labeled as 1. Okay, so let me just divide this screen here, and we'll take an example and then also give the two-step algorithm. Fine. So before we start, let me say that there are 5 alphabets or characters that are given to us, and for those 5 characters, what we are given is the frequency. Yes, so that means the A has a frequency of occurring as 0.35, B has zero point 0.1, C has zero point 0.2, D also has zero point 0.2, and underscore have a frequency as 0.15, 0.15. Yes, so what does it do is that if we are given any text, from that text for each of the character or the alphabet that is there, we need to find out what is the frequency. So once we have this frequency table, alphabet frequency table with us, then we can apply the Huffman tree. Yes, so the algorithm, what it says is, the first step here is initialize n node and one node tree. Yes, where you will have all the symbols of the alphabets are labeled there, and their frequencies are also included in its root to indicate the tree weight. So what does this mean? Initialize the n one node tree and then label them with the symbols, because there is one node, so that is the root node, and record the frequency as tree weight. Yes, so let's see what we are going to do in this case. So we have here, and when we are doing this, we have to put them in the increasing order of the weight values. So from here, the smallest value is B. So we are going to create a tree node, yes, where the root have the frequency and the leaf is the symbol. Yes, so record the frequency and label them with the symbol. The next one here is underscore, which is of 0.15. Sorry, I should write it above 0.15, and this is underscore. Then we have 0.2, that is given for C, 0.2 that is given for D, and then the last one, that is A, for 0.35 frequency. I hope the first step is clear. If you have any doubts, please do let me know. I hope you are able to see the blackboard as a full screen. If it is not, please let me know. Okay, so I assume the board is completely clear. Excuse me. Okay, let me repeat the initialization part here. So the initialization part here says that what we have to do is, for each of the symbol, we have to create a n one node tree. So we have n equal to 5 symbols here. For each of the 5 symbols, we have to create a one node tree. So this is one tree, second, third, fourth, and 5. Yes, and within that tree, we should label the symbol as well as record the frequency as the weight of the particular tree. So the complete weight of this tree right now is 0.1. For this one, because it holds underscore, so it is 0.15. For C, it is 0.2. For D, it is 0.2. And A, it is 0.35. Yes. Now, let's move on to step 2. So within the step 2, we have to repeat the following steps till we get a single tree. Right now, how many trees we have? 5. Yes. So what do we want is, we only want a single tree, a Huffman tree that will give us the complete encoding. So the second step is that find 2 trees with smallest weight. Fine. So we have to find a tree with the smallest weight. Now, if we have this weight values, so here what we have is these two are with the smallest. So what do we do is, we create a new tree for which the 2 previous trees become left and right subtree. Yes, and the node of that tree will have the sum of the tree weights. And then again we arrange them in the order. So if we do a sum of this, this will be zero point 0.1 plus 0.15, that is 0.25. So this 0.25 is greater than these 2.2. So right now you can have a concern whether the D should come first or the C should come first. So if C have come in that order, so we are going to keep that tree in the same order, because if we are implementing the algorithm logic into the program, so definitely whatever values is coming first, that will be kept first into the tree. Fine. So the resulting tree now would be this 0.2D, and after that we will have, sorry, we will be including 0.25, that is one new node. Yes, and the left tree is 0.1 and then B, and the right one is 0.15 and the underscore, and the remaining one remains the same. I hope that's clear. Yes, but we don't have to stop here. What it says is that we have to keep on repeating this till we get a single tree. So next again what we are going to do is select two trees that have the smallest weight. So in the next it will be this. And if you combine these two, 0.2 plus zero point 0.2, it will be 0.4 and it will be greater than both of these. So we will have 0.25 coming here, which will have 0.1 and B as the left, and 0.15 and underscore here, and you have 0.35 and A, and next you will get is 0.4, and what you will get here is 0.2 and C, and 0.2 and B. I hope this is clear. So this doesn't stop here again. What we will do is, again, because we have not got the single tree, we have to only stop when we get a single tree. We have not got a single tree, we have 1, 2 and 3. So right now we are going to combine the next two smaller ones. So let me erase this and put it on this side. Okay. So 0.25 plus 0.35 will become 0.6. So if we are putting it in order, so 0.4 will come first and then the 0.6. So 0.4 is here and it includes 0.2 of C and 0.2 of D. This one will become 0.6. 0.6 have the left node as 0.25, right node as 0.35, whereas this have 0.1 of B and 0.15 of underscore, and this one is, sorry, it's not a circular one, it's a single one. Yes, so 0.25 and 0.35 are combined and this is your remaining one. So these two are now left. So combining the two, what you get is 0.1 and then 0.4, this is 0.6, this one is 0.25 and this one is 0.1 of B, 0.15 of underscore, and 0.35 for A. And this one is 0.2 for C and 0.2 for D. Yes, so I hope this is clear to you. Okay. Yes, this one will be 1.0 only. Zero point 0.4 plus zero point 0.6 is 1.0. How many of you doesn't have the clarity of the videos? So the board is not clear, or board is not clear, or my voice is not audible. So I assume right now it is all fine, so I can continue. Okay. From here, what we get is this is called your Huffman tree. And in this tree, what we get here is alphabet symbols are the leaf nodes. So if you see here, C, D, B underscore A are all the leaf nodes, and the left edges should be labeled as 0. So all the left edges, wherever it is, we are going to label them as 0, and all the right edges should be labeled as 1. So I'm going to label it as 1. I hope that is clear. These are the 3 points. Once you have got the tree, how do we do the labeling? So all the right edges within the tree are labeled as 1. All the left are labeled as 0. Now from this, what we are going to do is, we are going to get the code. Yes. So to represent A, what do we need? So to reach the leaf A, you have to traverse through these edges, and these edges are nothing but 1, 1. Yes, to reach B, you have to traverse through these edges, and it is 1, 0, 0. To reach C, 0 and 0. To reach D, it is 0 and 1. And to reach underscore, it is 1, 0, 1. So what we have gotten here is the Huffman tree and the code. So this code, once you have this code table with you, then you can generate the code for any given text for A, B, C, D and underscore. Let's say we are saying that the text that is given to you is B, A, D. So to represent B, you have 1, 0, 0. To represent A, you have 1, 1. And to represent D, you have 0, 1. Yes. Now, if you see here, none of these have a, a code that is a prefix to the other code. Because within the Huffman tree, it makes it possible that none of the code is actually a prefix to the other. Yes. So 0, if it is there, it is single, it is not a prefix. Yes. So it is only going till the end, and then only it is generating the complete code. So in that case, it is not requiring any prefix to code. So let's say what happens when you have something like this, B underscore A. So in this case, B is represented as 100, underscore as 101, A as 11. So it clearly gives you the code. I hope till this point it is clear. If you have any doubts, please let me know. Okay. So from here we move on to what is the average number of bits required for the symbol. Yes, we have done it in the previous case when I have told you that let's say we have an example where A is appearing 3 times, E is appearing 2 times. Yes, so here A have a frequency of occurrence or probability of occurrence as 0.35. And A needs how many bits? Only 2 bits. Yes, so let's say what we are calculating here is average number of bits per symbol. Yes, to, uh, to find out that, so this will be equal to 2 into 0.35 plus Then B is having how many bits? 3 bits into 0.1 plus point, sorry, C is appearing for 2 bits. So 2 into 0.2. Again, D is appearing with the 2 bits. So 2 into 0.2 plus underscore is having 3 bits into 0.15. So what I have here is number of bits into the frequency. Yes. So this will be 0.7 plus 0.3 plus 0.4 plus 0.4 plus 0.45, which will be equal to 0.1, and this will be 1.5. So this will be 2.25. Yes. Now the average number of bits required here is 2.25, where some are requiring 2 bits, some will be requiring 3 bits, but the average is 2.25 per bit. Sorry, per symbol. 2.25 bits per symbol. Now this have, because we have used the variable length encoding, so this have done a compression to the complete encoding thing. So we will have a compression ratio here, yes, which is given by, okay, let's say in this case, if we are using a fixed length encoding, in that case, the number of bits required to represent each of the symbol is 3. Yes, so the compression ratio is 3 minus 2.25 divided by 3 into 100, which is 0.75 by 3 into 100. So the compression ratio is 25%. So we are able to reduce the number of bits, yes, by 25%. So whatever text you have, if you are using these symbols, yes, then it will be 25% less than the fixed length encoding. Yes, so that is your compression ratio. But here the drawback is every time once the encoding is done and you want to decode, yes, then you need this coding table. Yes, so for that, although it is not in your syllabus, we can use the dynamic Huffman encoding. And with this, let's move on to one more application of the Huffman encoding or this Huffman trees, where we can use some n number of positive numbers w1 to wn to represent the Huffman encoding. So let me share it with you how we can use that. So within here, we have talked about all of this, and we have taken this example. We have talked about the compression ratio, and now we are going to talk about the n number of positive numbers, how they can be represented so that the weighted path length is always the minimum. So let's quickly move on to the example that's given in your textbook. So let's say you are given some 4 integer values and you have to select any one of the 4, like either 1, 2, 3 or 4. So if that is the case, then for n equal to 1, n equal to 2, n equal to 3, n equal to 4 represent 4 different chosen numbers. Yes, so this can be used for where you have different choices for a game, 4 different choices. So which one have to be chosen? So how much path length should be used for that? So there are 2 representations of the Huffman tree given here, which is which is using decision tree to represent it. So decision tree is a tree where at every node you do you decide something. Yes. So if you see the first tree where we have n greater than 2, we have the 2 choices whether n is greater than 2 or not. Yes. If it is not, we move on to whether n is greater than 1. If it is true, then n would be equal to 2. Otherwise, n is equal to 1. Yes, because we are on the left hand side where we said that n is not greater than 2. If n is not greater than 2 and n is greater than 1, so definitely n is equal to 2. Yes. Similarly, on the right hand side, so I'm not going to give the explanation of this. It's uh, quite understandable. So in this case, what we need to find out here is what is the weighted path length. Weighted path length is given by summation of Li into Pi. Li is the path from the root to the ith value. Yes. So from root to the ith value, and Pi is the probability of occurrence of this. Fine. So let's quickly move on to the board and see what would be the estimated path length, weighted path length in this case. So if we have n greater than 2, then n greater than 1 and n greater than 3. Let me move back to the board. So this was there. This is no, this is yes, no, yes, no. And this is n equal to 1, n equal to 2, n equal to 3, and n equal to 4. And the other tree that we had, n is equal to 4, it says no, and it says yes, then n is equal to 4. Then it checks for whether n is equal to 3, again no and yes, then n is equal to 3. N is equal to 2, yes. So we have these two trees. Let's say the probabilities that are given to us, the probability of occurrence of the first element, that means n equal to 1, is given as 0.1. For the second one, it is 0.2. For the third one, it is 0.3. And the fourth one is 0.4. So let's try to find out what is LIPI for this I that goes from 1 to 4. So in this case, Li is the path length. To reach to the first element, you need two edges. Yes. So the path length is 2 and the probability is 1. And if you see here, the probability, the path length of 2 is also 2. Path length to reach the third value is also 2. Path length to reach the fourth value is also 2. So 2 into 0.2 probability of getting 2, 2 into the probability of getting the third value plus 2 into the probability of getting the fourth value. So this is equal to 2 into 0 0.1, 0 0.2 plus 0 0.3 plus 0 0.4, which is equal to 2 into 1.0 equal to 2.0. Now quickly let's see here. To reach to 1, you have to get 1, 2 and 3. Yes. So 3 into 0 0.1 plus 3 into 0 0.2. So to reach to the second value, you need 3 again decisions. So 3 path length into 0 0.2, the probability of 2. Sorry. Yes. And then to reach 3, you need 2 path length and the probability is 3.3. And for 4, you need only 1 into 0.4. So this becomes 0.3 plus 0.6 plus 0.6 plus 0.4, which is equal to 1.9. So the complete path length, yes. So in this case also, if the probability is more, we are creating the tree such that it has lesser number of choices. So in that case, we get a better solution at the end. So this kind of a tree where we are trying to find out the weighted values from the given tree, which is an application of your Huffman trees, whichever have a higher frequency, we try to have a smaller code or smaller path length